Can you join the Zoom link? Yeah, I don't know why the audio is not working. It was working. There is no audio. We can't hear anything. So, yeah, it's still- I don't know. You can hear it. Zoom का है. सुनने जाता. अरे वेबसाइट तो खोल भाई. एखाনে वेबसाइट. No, वेबसाइट पर खोल नहीं. So right now, we were we noticed that we are going to अभी पता चले যাচ্ছে Hello. Wait. What is the problem, man? That's the thing. Just come on again. I get the recording.
there is a greater role. And therefore, these days the students are not, it's just interested in studying. It's a difficult to have in the department. And there is probably most languages of that. I don't know if it's a very interesting mind to realize it. How interpretation is in sciences and it's discussions around mathematics in mathematics. And tomorrow, when a person like mathematics will not say that this is how to appear. So, I think for us to
kind of operation.
and I sincerely hope that if you capture the expectations of the nation, expectations of today's answers, in the place which avoids the no, so that's good. It's only what we are. Not only to tolerate in these words, without food, and unfortunately, by itself, as you go for I want to mention in the celebration of the thank you for your inspiration to do more. And we hope we have more so thank you very much for the kind work. Now we are going to make two announcements. Evening we are so we will have a cultural program is essentially some and it will be followed by a special
Thanks, Vaibhav. I'd like to thank the organizers for inviting me to speak on this occasion. It's a real pleasure to speak in honor of Kapil Paranjape, somebody I've known a really long time. We kind of learned algebraic geometry together, I would say, in a way. I first met him in 1980 when I was a graduate student and he was an integrated MSc student in IIT Kanpur. I gave him a private lecture on the whale conjectures in the aerodrome in IIT Kanpur, and so on. We had a very nice time there. Then later, when I came to Tata Institute as a postdoc, he was had joined as a graduate student. Spencer Block taught a course on arithmetic class field theory for, and Kapil was a note taker, so we had a lot of. Then did mathematics together, we learned things together, did other things together. Anyway, it's a pleasure. Yeah. Recording wise, they're okay, they said, but people can't. Yeah. Okay. Can you hear me now? Oh, good. Good. Should I get started? Okay. So the context is the following. Let X be a connected variety over an algebraically closed field K, and I want to consider its Étale fundamental group, which I'll denote in this fashion. I'll just write pi1 x. I might write pi1 Étale x. Okay. And I'm going to omit the base point. It's not very serious for the considerations at hand, and so it doesn't matter. I won't give a formal definition of this thing, but I won't tell you. Consider, so to speak. These correspond to group quotients pi1 Étale x to G by open subgroups. And the quotient should be topological quotient. So the way you study this thing is by studying the group pi1 Étale is through its quotients, and those quotients correspond to something in geometry, and the geometry side is what you study. So that's the Étale fundamental group. Let me remind you, there are some theorems that if K is the complex numbers, there exists what one calls a comparison isomorphism. So if K is the complex numbers, then the complex points of X are also a topological space with a classical topology. So there is a fundamental group which is constructed in algebraic topology using paths and homotopy classical groups and the like. That I can call pi1 top of the complex points. Then there's a group theoretic operation called pro-finite completion. So this hat is the pro-finite completion. So if you have gamma a group, then I can associate to it gamma hat, which is the limit gamma onto G G finite of G. Take all finite quotients of gamma and take the inverse limit of those things, and gamma maps to that inverse limit in a natural way. That's a kind of completion of gamma in some sense, and that's called gamma hat, a profinite complete. So this is take the topological fundamental group, which would construct an algebraic topology, do this group theoretic construction, you get the Étale fundamental group. And the algebraic geometry assertion behind that is that if you took an algebraic variety over C and took a finite degree Galois covering space in the sense of algebraic topology, there's a unique way of putting an algebraic structure on the domain of that covering, the total space, so that the map is a morphism of variety. An Étale morphism. The so-called Riemann generalized Riemann existence theorem is what it's called in the English or other literature. The Germans say this is Hebbard-Feitz. It's not existent. It's Riemann's singularity theorem. Anyway, whatever it is, it's a theorem. So we have this. So a consequence is that phi1 at x is finitely presented as a profinite group. And the reason is we know something from algebraic topology. Phi1 top of xc is a finitely presented group. As an abstract group. For example, one knows that the variety, the xc, the topological space, has the homotopy type of a finite CW complex. So all sorts of invariants I can cook up from algebraic topology have intrinsic finiteness properties, and the fundamental group is one. Okay. So this is characteristic 0. Similar conclusion holds. Similar conclusion. I mean, this is the characteristic of K is 0. It doesn't have to be the complex number because there are some standard theorems which compare a general field of characteristic 0 with the complex number. And let me not elaborate on it. So this sign over in characteristic 0. What about in characteristic P? So phase if the characteristic of K is positive in general. There's an obvious one standard counterexample. Take the Étale fundamental group of the affine line over K. I claim it's not even finitely generated, let alone finitely present. And why is this? Because I can look at the following thing. I can look at form of phi1 Étale A1K abelianized tensor Z mod P into Z mod P. And if this group was finitely generated, then this abelianized group would be finitely generated abelian. Tensor Z mod P, it would be a finite group. Form of finite group into Z mod P is certainly finite, but I claim this thing is isomorphic to the so-called first Étale cohomology of the affine line with Z mod P coefficients. And there is a formula for this. This is the co-kernel of takes the map from the polynomial algebra on one variable to itself, which sends a polynomial f to f to the p minus f, and take the co-kernel as an abelian group. And the claim is this Étale cohomology is isomorphic to this, and then that in turn is isomorphic to this. And this is certainly not finite. This isomorphism is from something called Artin-Fryer's theorem. So, in characteristic 0 or over complex numbers for any variety X, the fundamental group is well behaved. Here, for something like the affine line, which in characteristic 0 would have been contractible and has 0 fundamental group, is not even finitely general. Okay. So I can't expect the same results in characteristic 3. On the other hand, I claim there is something which is not so bad. There's the following theorem. Go back to the velocity. So from now on onwards, okay, maybe I should say that. From now onward, let the characteristic of K be positive and let P be the characteristic. And I might have to consider the prime P as well as other primes. The theorem, let X be normal, for example, non-singular, and projective. Okay. Then Y1 étale X is finitely generated. One thing which went wrong here is X is not projected. The affine line is not projected. Once I make it projected, finite generation is okay. And let me sketch an argument for that. Probably did this in courses fiber took from me. Well, not quite. I've done part of it, not everything. I'm not particularly hot. So, true. So let's see in X be a smooth complete intersection curve. So even if X has singularity, if it's normal, its singular locus is in codimension 2. That's one of the properties of normal. It's not very singular. It's only singular in a small dimensional thing. So if you took a complete intersection curve, that's going to avoid the singular locus completely. It's possible to make it non-singular by Bertie and so you can always find such a thing. Then let's assume now I was thinking of broken bits. So let y to x be a connected G Galois curve. So then let's write a diagram like this. We call this F, and this is F inverse C. Let's take the inverse image of C in this covering, and then I can write a diagram like this. Notice then that C tilde is a non-singular curve. In Y, which is a complete intersection of ample effective Cartier divisor, which implies C tilde is connected. This is the thing I might have done in the algebraic geometry course I was talking about, which is lemma of basically an ample divisor is connected. This is a theorem on vanishing of cohomology, and so and it follows from shared duality. It's in Archon's book. So relatively elementary algebraic geometry implies this property. But if I translate this into covering, it's saying if you took any covering of a wedge, a Galois cover, and restricted it to get a covering of C, it's still connected. This implies this is the same as saying that pi 1 étale of C maps onto pi 1 étale of X. Every connected cover here restricts to a connected cover. So I'm trying to prove finite generation. If I can prove this is finitely generated, I deduce that that is finitely generated. And so finite generation has this aspect. So therefore, we reduce to, I'm trying to prove finite generation, reduced to the case X equal to C is a smooth projective curve. Now we have the less elementary part of the argument, which involves something called lifting to characteristic zero, which is also one of the things I want to discuss later in the talk for other reasons. So let me spend a little time talking about it. As a kind of aside, recall a smooth, let's say, proper variety X over K. Well, smooth and proper are not really required, but it's good enough for me. Opposite. Lifts to characteristic zero if there exists a complete discrete valuation ring A with quotient field K of characteristic zero and residue field which is K, which is of course of characteristic P, together with a smooth proper morphism X to spec A whose closed fiber is isomorphic to X over the residue. So the variety X over little k lifts to characteristic zero if there's some script X mapping to spec A, which is kind of like a family of proper schemes parameterized by spec A, where over the close point, I get the given variety and for the general point of view, I get something in characteristic zero. Then there's a theorem of Grothendieck. Before I do that, let me discuss very briefly one thing. If X is smooth and projective, and I have certain conditions on cohomology, H2X of the tangent sheaf of X is 0, H2X of the sheaf of functions on X is 0, then there exists a projective script X respect A, lifting X to characteristic 0. This is part of standard deformation theory, that there are some obstructions to constructing these deformations. the obstructions may be 0, but in fact, if the obstructions lie in some co-only, the co-only is 0, all obstructions are 0. So this implies that curve C, for which I wanted to study the fundamental group, has the property that that curve C has vanishing H2 of the standard sheaf and H2 of the structure sheaf because the dimension of C is 1. The second co-only of anything is 0. So C lifts to characteristic 0. Now, under these conditions, Grothendieck proved the following important theorem on the fundamental group. It's called specialization of the fundamental group. So let script X to spec A be a smooth, proper morphism with closed fiber X. Then it's possible to make sense of the Étale fundamental group, even of this scheme X, and it's in fact isomorphic canonically to the fundamental group of the closed fiber. So the way to think about it, the way to understand what it's doing, script X is some kind of tubular neighborhood of the closed fiber, and if everything works nicely, you ought to have the same homotopy type. The homotopy type of the fiber should be the homotopy type of a small enough tubular neighborhood, and so if we believe that that intuition works, this is the sort of thing we would guess. Any case, that's theorem. 2, remember K is the quotient field of A. Let me say if K in C is an embedding, then phi1 topological of the base chain scheme to the complex numbers, take its complex points, take the topological fundamental group. I can take its hat to make an Étale fundamental group. There's a map to phi1 Étale script X, which is phi1 Étale X by part 1, and it's surjective. Yeah. Didn't I assume it's a complete linear? As above, I could say. As above. Right. Right. So there is a map from the profinite completion of the topological fundamental group of the lifted thing to the fundamental group of the special fiber, and it's surjective. This is the theorem of profinite. Surjective is fine for finite generation questions. If I want to prove this is finitely generated, if that's finitely generated, I'm fine. But this is something about complex numbers. It's finitely presented. So certainly this is okay. Anything which lifts to characteristic 0, certainly its fundamental group is finitely generated. So curves lift to characteristic 0. Therefore, for curves, the fundamental group is finitely generated as an profinite group. I believe there's no other proof of this known except by lifting to characteristic 0. It's a pure characteristic tree assertion, something about covering, and there is no proof except using the Grothendieck question. Understand? I believe, for example, Abhyankar tried very hard to do things like this before. Grothendieck came along with this machine and did this, and Marx Abhyankar was not very happy. I'm told. No, curve. Curve it was not now. That's the point. You have to do curve. And do curve, you can do anything. That's what I'm saying. Elliptic curves must have been fine. Let me give you another notation. I haven't finished it. There's one more thing I'm trying. Okay, so let me write the conclusion and then explain the conclusion. Further, if I look at y1 topological xc, this thing which I cooked up over complex numbers, take its profinite completion and then put a bracket p there, where p is the characteristic. This maps to the similar thing here. This I claim is an isomorphism. So what is this bracket p notation for a group gamma? Let gamma but p be the inverse limit it's like profinite completion. I take an inverse limit over quotients, but I put an extra condition that p doesn't divide the order of the quotient group. Among the quotient groups, some of them may have order relatively prime to p, others divisible. And so I exclude the ones where p divides the order, take only the quotients where p doesn't divide the order, take the inverse limit over that for a smaller system. Whatever I get is a kind of completion with this bracket p there. So if I said here that there's a map here, it's surjective. And in addition, if I take bracket p on both sides, it becomes an isomorph. Grothendieck proved these things. Right? The prime to p completion is isomorphic, but the actual thing is only surjective. Okay. Note that, of course, by passing through this thing, you lost a lot of information. For example, if you have a quotient like the symmetric group or the alternating group on n letters, and n is large enough, p is going to divide the order. And there are lots and lots of generic things you write down. The Galois group is going to be Sn, you would expect. Right? So there's lots of stuff you just threw out by passing through this p. You've got a lot of information retained, but a lot lost at the same time. So it's not quite clear what you should be thinking about, what you should say about the structure of this. Anyway. Sorry? Please wait. You didn't read my abstract. Okay. So let me make a remark. I do not know an example of a smooth projective curve C, let's say ft bar, or any k of characteristic p of genus at least 2, for which there is an explicit presentation for the fundamental group. It is finitely generative. It is a quotient of the analogous fundamental group for that genus in characteristic 0. But what the kernel is not clear. What the relations are not clear. There's no example for which this is computed as far as. And in fact, there is a comment in SGA that we just give a reference for those who want to read that thing. Look at SGA 1, expose 10, section 2.8. There's a statement there in French. I did a Google translate. It says it's entirely improbable. That's what Google says as a translation. This is what the statement is. So SGA attempted to give a guess at least for Rajan's question. Yeah. Wait. At the end of my thing, if I haven't answered the question at that point, then I want to report one theorem that XD is a pair consisting of Schusterman. This is COVID time mathematics. I meant to say. Not even over. Both that person and I have collaborated with Ellen and we exchanged emails. I'm not really into Zoom. Zoom is okay for committees. The mathematics, I find I'm too old. Let's take a smooth pair consisting of smooth projective variety and an SNC divisor, a simple normal crossing divisor. Usual thing in algebra. Then it's possible to define something called the tame fundamental group of the pair X comma D. This is finitely present. As per finite group. In particular, phi1 Étale X is finitely presented if X is smooth and projective. That's the case D equals NT. At T equals 0. And a corollary written with Lara and Jacob Sticks. It's really a corollary. It says that phi1 Étale X is finitely presented if X over K is proper. No. Well, connected. Otherwise, I have to say that connected component depending on where X over is. And the idea is that if you can do the smooth projective case, then there's a kind of argument, a descent type of argument using an alteration and a kind of version we were talking yesterday about Van Kampen's theorem being a statement of descent. So strict people understand that thing very well, and that machine allows you to deduce the finite representation for an arbitrary X from the smooth projective case by this thing. What's tame fundamental group? It's something where I look at coverings, I look at the Étale fundamental group of the complement of X from allowing ramification along B, but that ramification has to be tame. So there's a notion of tame, particularly in higher dimension, you have to think a little bit what it is and some choice and so on, some discussion. Let's not get into it here if people want that. So this is what it is. Yes, because there's no, it's the empty set, so the ramification, there's no ramification, therefore, whatever ramification is there is thin. Vacuously. We don't know whose intuition this is. It's in SGA. Grotharik is, of course, the main author. Once it's wrong, of course, I don't know whether to attribute it to Grotharik. Anyway, doesn't matter. It's assertion in SGA. They don't say it's not correct. It says it's improbable. Yes, and it's not counter to this, you see. This is saying I can't write a formula At least we don't know. We don't have even a single example where we can compute it. No. Only for the 10. The moment you remove points, you're in real trouble. That's what I explained right in the beginning. Unless you get rid of wild ramification, some fashion you have to. Well, it's not to say you can't do anything, but then you have to reformulate things, find the right questions, and then there are interesting questions there, which people are trying to investigate. Okay. So this is one result I want to discuss with you. A little bit, I'll say what goes into the proof. I want to also mention a second thing which comes again out of the same business of growth theory, of lifting and specialization. It's natural to ask, is it the case, since I know, let's say phi 1 x is finitely presented, can I find a finitely presented group by some method whose profinite completion is the phi 1 x? Is there any reasonable way of constructing such a thing? Maybe more than one, maybe whatever. By the way, it is the case. It's possible to construct X with different liftings to characteristic 0, where the fundamental groups you got in characteristic 0 are mutually non-isomorphic for different lifts. You can take the old example of fair, and you can show that in appropriate context, you can get an example of that kind from you. Yeah. It's not been computed. Well, the tame fundamental group must be the obvious thing, right? That's correct. There you can compute. Yeah. The tame fundamental group is the natural. Yeah. So bracket P or there'll be some condition. Tame, right? Tame. That's the point. Once you made it tame, everything looks like the puzzle. Well, many things look like the puzzle. There are still things which can go wrong, but they're more tricky. Now, from Grothendieck's theorem, the one which I just erased on specialization of phi 1, implies if X lifts to characteristic 0, then phi 1 at X satisfies a certain group theoretic property. It will be a bit complicated, but maybe right now. Like this, a finitely presented group gamma together with a homomorphism from that abstract finitely presented group to the Étale fundamental group. That's that. For any if I take any open normal subgroup U of the Étale fundamental group, and I will take some finite group quotient of phi 1 Étale, which is compatible with the topology, and then take the kernel, that's a U. No, this is abstract, this is profile, never going to happen. But it's got a suggestively type property, which is this coming. If I take an open normal subgroup in phi 1 et al., pull it back to this gamma, this abstract group gamma under that homomorphism. That gives me a gamma u, a normal subgroup. Gamma mod gamma u maps to pi1 Étale x mod u is an isomorphism. So this will imply that gamma hat to pi1 is surjective. I might as well also say gamma u hat also surjects onto u. Inverse image of a normal under a homomorphism. Because it's not surjective. That's the problem. Thank you. Now, what is the problem? Yeah. Of pi1 mod u is the question. Meaning there's a natural homomorphism gamma to pi1 mod u. The kernel of that homomorphism is gamma u. Being kernel of a homomorphism is normal. Yeah, gamma u hat p is isomorphic to u p. So all these things follow. So what is this saying? This is saying the same thing. Whatever I said about the Étale fundamental group of X and the lifting is valid, but it's not just valid for X. It's automatically valid for the collection of open normal subgroups of pi1 Étale X in a compatible fashion. That's extra information of a group theoretic kind. That's the point. That's extra group theory information. And I can exploit it. So I claim this is, if X lifts to characteristic 0, the Étale fundamental group as a group must have this group theory property. There must be an abstract group gamma with a homomorphism, which simultaneously somehow understands all the open normal subgroups in some fashion, in a compatible way. Therefore, I claim this group theoretic property could provide in principle an obstruction to the existence of a lifting to characteristic 0. And that's the theorem I want to report next. That's all. Projective also I assume. Yeah. Proper. I could have, I suppose, but I want gamma to be abstract for some reason. Yeah. So can it might be okay also. Yeah. But it's good to formulate like this because I'm going to say, give an example where this condition fails, but part of it will fail. And maybe you can give another example where some other part fails. I mean, once gamma is actually finitely generated, it has other finiteness properties of its representation, varieties, and things like that. Maybe you can exploit those things also in some pattern. People are trying to do stuff like that. So let me write that. Theorem. The exists smooth projective X of characteristic P for which pi1 at X does not satisfy this group theory condition stuff. And corollary for this X, there doesn't exist finitely presented gamma with gamma hat. What that means is that for certain varieties X, though the Étale fundamental group is finitely presented in the pro-finite category, and it does have finitely many generators in the natural sense, the relations, there are finitely many relations in principle, But the relations could be infinite words in the generator, which are kind of topological words which converge in the finite topology. And you're forced to write to the. And then the other aspect of finite presentation is that you have to take the normal subgroup generated by those finitely many words and then take the closure. Closure introduces lots of stuff in the profinite topology. So that's why you're able to get a theorem like this. Anyway. Nothing. Anyway. What is the dimension of the X for which this is true? Well, in the end, I'm proving something about its fundamental proof. So you can even in the end make X a surface by the Lefschetz theorem. I'll construct an X of some dimension, but then you can replace it by a surface to be self-side without changing. Curve you can't do. Curve do lift to characteristic 0. Okay. So let's see what's my time. Let me just say 2 words about what goes into the proof of that. How are you able to manage that when you can't do any computation? So the point is to use, first of all, there's a kind of Lefschetz. So I'm now discussing the proof of this first. And then briefly, I'll say what's the example. So there's a kind of Lefschetz theorem. This is due to Eno and Kindler from our group in 2016. Phi 1 at of Z intersection D. Let me just vaguely say satisfies. Not Phi 1, Phi 1 K. There's a standard Lefschetz theorem, which is true topology and so on. If the Z has dimension, Z is a complete intersection inside X, Z has dimension at least 2, it's an isomorphism. Z has dimension 1, it's like and that. It's surprising that for the same fundamental group, 2016 is when this was published. Of course, maybe sure people like Reno and so on knew how to do it, but it wasn't in the literature. You can, but it's a better result with the D. Right? Then I'd use the classical group. Absolutely. You can do that. Absolutely. Absolutely. And it's not like the proof of this uses some fantastic new thing, but just that you have to go through the technical stuff and check that it all works and patching and happening. But it's no surprise. There is work to do. You can do. So what's the new ingredient really is the following theorem, which I didn't know about, some theorem from group theory. What he proved this in 2001. Let gamma be a finitely generated profinite group. Then gamma is finitely presented as profinite. If and only if there exists a constant C greater than 0, so that for any finite abelian group M with continuous gamma action, take log of the cardinality of the second group cohomology of gamma acting on M, that's bounded by this constant times log of the cardinality of the model. So this is the criterion of the box. It means that in the category of profinite groups, it's a finitely connected object. In other words, if you look at the relation, so you've got take the closed normal subgroup generated by those finitely many expressions that is there. And the important thing is you took closure. So you introduce lots of stuff in the relation, not merely with quantitation, but also with closure. Right. So then, given this, if you have one of these m's, and if you have well, okay, if gamma is supposed to be pi1 eta x or pi1 tame xd, then and m is a gamma module like that, then there's a sort of mx, a local system on x, an Étale local system, and one can show h2 gamma m injects into h2 Étale x mx. So then the problem of bounding the order of the second group cohomology is reduced to the problem of bounding the second Étale cohomology. And that you have to do with algebraic geometry method. Let me not elaborate on it. It's not super difficult. It uses rail conjectures, things like that, but you know, there's a huge lot of information about Étale cohomology out there. Particularly in the case where no D directly follows from wave conjecture type things. When there is a D, you have to do more. But there's a theorem of Deleuze. It says something about chi of a local system with same ramification at the boundary is equal to rank of the local system times chi of the trivial local system. Using this, and then we can do it. So what about the star business? This thing, let me give the example. That's a fun example. So let me just make the following condition about star. If that condition star holds, and I have one of these U's, and G is the quotient, because the condition star then an abstract group gamma, and it had its own normal subgroup, and the quotient was again the same G. G is realized this way. I know further that I can look at gamma U abelianized tensor ZL. This will be isomorphic to U abelianized tensor Z hat ZL for all L different from P, since gamma hat P is isomorphic to UP. I'll get such isomorphisms as G module. And this is the point. So I think of this as a compatible family of L-adic representation of this finite group G for L different from P. And the question is, if the condition star is satisfied, it comes from a Q representation, a Z representation even. So that's a number theoretic construction. If I have a compatible family of L-adic representation, then even if I know that all the characters take values in Q, it doesn't necessarily follow the representation is defined over Q. There's some obstruction in the Brauer group. And you can find an example where that obstruction is realized and is non-zero. So there's no underlying Q representation. Therefore, this is important. That's going to be good. And the example is the following. You take our X is going to be something like this. I'll take a curve over FP bar, cross over FP bar Z. And C FP bar is C cross over FP bar for a certain curve C over FP. C is what's called a rocket curve. So it's a curve given by y squared equals x power p minus x. And I'm going to assume for this purpose that p is at least 5. This is a hyperelliptic curve. So branch cover of P1 ramified at all FP rational points. The branch locus is invariant under the full projective group. Therefore, the curve has lots of automorphisms, and you can find G equals aught C FP bar has the property that its cardinality is 2p into p squared minus 1, which is greater than 84 times p minus 3 over 2, which is 84 times g minus 1 in this example. So this is one of these curves which is known to violate the Riemann bound on automorphism. To take this curve, let Z be a smooth projective, smooth complete intersection with free G action. Now we do a Serre construction. We just do X to do the product with a diagonal G action. Sorry, mod G. I haven't said what G. And then I'll ensure that G, the fundamental group, fits into an exact sequence. Fundamental group of the curve maps to the fundamental group of X, maps to G, right? By construction. And G sort of acts on the fundamental group of the curve in the way it acts on the curve. And therefore, it acts on the Jacobian. The action on the Jacobian tells me what the Abelianite fundamental group action is. And so I can compute that. And one finds here the Jacobian of C FP bar is isogenous to e to the p minus 1 by 2, or e to the whatever, e to the n, the correct number n, where e is a super singular elliptic curve. Yeah, G. N is G. G is something. It's whatever is consistent to this form. Okay. I think that does it, right? There is such a thing, and it has the properties I claim, star cannot be signed. Yes. In the profinite category, gamma is an abstract profinite group, meaning the relations are finite words in the generator, as opposed to topological words, which is allowed in the profinite category. That's the difference. So it's saying such an X would need the genuine infinite words. There's no other way to do it. That's why you can't write a presentation. Actually, we are not planning. It's finally presented in the correct category. Thank you very much. Mm-hmm. That's right. This is a tame covering of P1. Yeah, exactly. And then take the Étale fundamental group of this is that. Well, it's not exactly the. How do I say that? You're saying those coverings are tame. Yeah, that looks correct. So even the tame fundamental group looks badly there. That's it. That's it. That's it. That's one of them. Here's the graph. There are all sorts of weird things on fundamental groups and characteristic fields. I think people haven't really explored, especially after SGA more or less says it's impossible. Nobody tried that. It's not very much. There are weird things. If you take a family of smooth curves, specializing non-trivially in moduli, there's a specialization of homomorphism on phi 1, which apparently never an isomatic. If the corresponding modular thing is a non-trivial specialization, the induced specialization on Étale fundamental group is not an isomatic. It's a field. Come on. Okay. Exactly like in Sayre's paper, you give a general concept. Any finite group, we no. Okay. Take any faithful representation of B, take the direct sum of the copy of that faithful representation with itself large number of times. Then you see the induced action on projective space, locus were non-trivial isotropic. The codimension tends to infinity. Then okay.
Um, so I've asked the same question when you were at TIFR. How much can you comment on the Nori fundamental group scheme?
I'm the wrong guy. After the next talk, maybe the speaker is more expert on those things than that.
So
this will be joined to our reporters and joined to our to base. Yeah, to base. Okay. So let's begin. X is a compact Riemann surface. Compact connected Riemann surface. E of X, I take rank R, degree 0, holomorphic vector bundle. E is called stable. If degree of F is less than 0 for all holomorphic subbundle, F F of E. Okay, so there is a moduli space. Moduli space of such bundles, stable vector bundles. Of rank R. I'll always consider degree 0. Rank R degree 0. Now, how the modular space looks like? So there is a well-known theorem of Narasimhan and Seshadri. That theorem says that any stable bundle, all stable bundles, a stable bundle, E of this kind, admits a unique unitary connection, that connection. So M is identified with home phi 1 x comma x naught UR quotiented by UR. Quotient means UR acts on itself by conjugation, so it acts on the homomorphism space. Yeah, I'm taking the quotient. Sorry. The unique unitary connection is automatically irreducible because the bundle is stable. So this identification is irreducible with irreducible connection representation. So it doesn't depend on the choice of the best point because any two, if you take another best point, then two fundamental groups are uniquely identified up to inner automorphism. So inner automorphism is
of inner automorphisms, not one inner automorphisms. So when inner automorphisms are killed by this interaction, so it doesn't depend upon it. So you know the M topologically. Now using Hodge decomposition of unitary local system, you can construct a complex structure on it. M. So M becomes a complex manifold. Now it's a non-trivial fact that it is also an algebraic variety, smooth quasi-projective algebraic variety. Variety of dimension R square G minus 1 plus 1. G is the genus of X. I'm talking about stable bundle. So, and I'm talking about unitary representation. So, I should assume. Otherwise, there's no stable bundle of degrees. Anyway, so now some basic facts for any E, T of E, M at E is given by H1 of X and D. This is basic deformation theory. So now by state duality, H0 of X and D tensor Kx, where Kx is the holomorphic cotangent bundle. Holomorphic cotangent bundle. Of X. So now I'll define dot surface over M. Holomorphic cotangent bundle. So T over M is a algebraic fiber bundle on which T star M acts fiber wise. So we have action T star M. Then we write two action on the right, B and B times for M. B. This is action fiber wise. So that the action is P and transitive, which is written to give a name to this map action of phi. So B tensor times M over T star M to B times phi product over M over B. So this is the first map is the phi and second map is the projection. P onto the projection of the sorry, projection of the first vector. So this is an isomorphic. So this condition is same as saying that the usual saying that action is P and transitive, which is formulated this way. This is a standard way to saying that action, but this just means that the action of this is P and transitive. So So fibers of G are isomorphic. But not in linear way. There's no linear isomorphic up to affine. Okay. So now I'll study two examples of torsors. So the first example will tau is a theta character. Right? That means tau is a holomorphic line bundle of degree G minus 1. Degree of tau is that. Tau consisting per 2 means isomorphic to units. Holomorphic potential bundle. So now we define M, so we subset S on E in M. Such that H naught of X E tensor tau not is continuous. This, let us consider this. So note that Euler characteristic of E is 0. Psi of E H naught minus H1 of E is by Riemann-Roch R square G minus 1 plus this is the G minus R into G minus 1 minus R into G minus 1 equal to 0. So H naught is equal to 0. H naught of E is equal to 0. You can only H1 of E is equal to 0. So I'm considering alignment with vector bundles in M with vanishing homology. So now it's a fact that S is a divisor. It's called a theta divisor. So I didn't call it theta because I want to use the notation theta for the line bundle. This is a theta line bundle. So recall that we are in the process of constructing a torsor for this. First example of torsor. So now I'll construct connections on theta, sheaf of connections on theta. Connections. Yeah. So let us recall the definition. So we have a short exact sequence 0 going to holomorphic differential operator of degree 0 from theta to theta, which is just collinear homomorphism, that is O of M. To give one differential operator of order 1 from theta to theta. And second, the final form is a symbol map. So home theta to theta tends at TM. So by home theta to theta is a trivial bundle. So this is called the ATIA exact sequence for theta. We recall that a holomorphic connection on theta over some open set U is some open set, is a holomorphic splitting. Splitting of the exact sequence over U. So that means if you restrict to U and there is a homomorphism from U to this, such the composition is identity. This is a splitting that means you are writing as a direct sum. taking homomorphism, composition, identity, the holomorphic splitting. They are basically precisely the holomorphic connection and a infinity connection, a complex connection, sorry, complex connection on theta is a infinity splitting profile. A infinity splitting are precisely the complex connection on this line bundle theta. You recall that the connection is called complex. If it is a usual connection, I mean the real connection such that the del bar of the line bundle, holomorphic line bundle coincide with 0, 1 corner of the connection. I mean the connection is compatible with the complex structure. And holomorphicity, of course, is much stronger class of connection. That means it takes a holomorphic section of theta to holomorphic section of theta tensor omega 1, which is one level stronger connection than complex connection. Okay. So now we reformulate this exact sequence slightly differently. The splitting of this exact sequence is same as splitting of the dual exact sequence. So if you take the dual, so it becomes 0 going to this theorem going to be 1 theta star OM. So splitting of this over any open set or global splitting, whatever, is same as corresponding thing about the dual sequence, which is here. Let us call this sigma. Now M this trivial bundle has a section given by the constant function 1. So let us call it 1 M. Constant function gives a chief of function section. So now you take sigma inverse connection theta is defined to be sigma inverse of 1M of. So you take the map M, consider this section, look at the image of this section and take the inverse image of this inside this object in the bundle and call that con M and consider its projection. Now note that splitting of this over any open set is same as giving a section of giving splitting of the star over any open set U is same as giving a section of con theta over. So this both in holomorphic or algebraic or infinity category. Infinity section is giving a infinity splitting is same as giving a infinity section. Holomorphic section. Holomorphic splitting is same as giving a holomorphic section. Algebraic splitting section. So this is a kind of loosely speaking is called sheaf of connection, but which may not be correct statement. It's not a sheaf. But it kind of parameterizes sections of this at the precise the connection. Now we have got our torsion. torsion. Because now look that inverse image. Now this acts, right? If you add anything from here, it doesn't, it goes to 0. So when you write as an inverse image of 1, this acts spirit and this. So this is a on theta over m is a this diagram. This follows from the because those who are going to 0 is precisely. So now let us analyze a little bit. We'll do a small analysis of that. We mentioned that sections of this is same as connections on theta. So let us see what connections it has. Just a couple of remarks. One remark is that if I restrict theta to m minus s, so recall that theta is by definition O m s. So then this is same as O theta known O m minus s. Theta is a section given by the constant function 1. So this is a section. So this is a section. This is a. So this is the connection on trivial bundle given by the theorem differential D. So I'm identifying this, and this transports to a connection on theta. So this corresponds this any sorry what I've written. This is a constant function 1, and then so it gives a. I'm not looking at the section of this. So this gives a trivialization. This identity it's a trivial. So it has a section given by the connection given by the theorem differential. So I'm looking at this. This is my notation is. So this is the section of this. So section means a connection. Connection means which connection? This is identified with O, and it has the theorem connection given by the theorem differential. I'm taking that connection. So that section I'm calling it T. Sorry. This is defined only on m minus s. It doesn't extend to m. It extends the connection, the theorem connection on theta on O given by the theorem differential extend as a logarithmic connection, becomes a logarithmic connection. So it is not it's a singularity. So, but I'm not looking into singularity. I'm looking on m minus s. So now I'll quickly go to quickly mention another section. There is a well-known construction of Quillen on the connection of Hermitian structure on determinant bundle. I'll not go into that. Quillen constructs the Hermitian structure of this line bundle. So any Hermitian structure gives a infinity complex connection. So that means what I only want to say that Hermitian structure on this. So Quillen Hermitian structure will give a Hermitian connection on this bundle. So that means Quillen has given a infinity section, which is sorry. Oh, no, sorry, all of it. So that's most important. Okay, thanks. I'll call it Quillen. Q. So there are two sections. This is algebraic. This is only C infinity, and this only defined on a open set, and this is defined everywhere. I'll now. This is my first example, and I'll come to the second example. So remember, I just remember this picture. I'll be using this. This is omega this term torsion, and it has two sections. One is algebraic, one is infinite. One is defined for entire, and algebraic one is defined on the complement of the theta divided by that. Complement on S is on the theta divided. No, 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 no. Parvez, I absolutely think it's section. No, no, no. We'll come to that. It's a completely thinking. Okay, now take define CM modular space of E comma nabla where E is in M. Then we have already this means E is a stable bundle of rank and degree 0 and nabla is a holomorphic connection. E is degree 0 and stable. Stable implies it is indecomposable, and there is a theorem of Atiyah and Wells that any a vector bundle, an indecomposable vector bundle of holomorphic vector bundle of degree 0 admits a holomorphic connection. So every E in M admits a holomorphic connection, but the Narasimhan-Seshadri theorem is much more fundamental. It says there is a unique unitary connection. It has many connections. It has many holomorphic connections. Its dimension is same as R square by G minus 1 plus 1, but only among them only one is there. Anyway. So now we have the projection map CM to M. Not what so E common nabla is mapped to E. So just standard, just forget full map, I'm taking projection. But now note that it is a T star M torsor because any two connections, to space of connections of holomorphic connections on E is an affine space for H naught of X ND tensor of X, which is same as T star of E over M. So any two holomorphic connection on E differs by an element of the cotangent space. So it is a torsor for the cotangent bundle. So this is a torsor for cotangent bundle. You can just, it is very clear that this connection is satisfy the Leibniz identity. So if you take difference of two connections, the non-linear, non-linear part cancels off and gives a current section of entity. So now this has which let us consider section. So the CM over M is forgetful map. This is a well-known section that is that the Narasimhan-Seshadri connection that gives a section. Let us call it NS. As I said before, every stable bundle has a unique unitary connection. So I'm just associating that unitary connection. So this is a infinity section. It's like a totally real. Because after all, you cannot expect to be any holomorphic property because unitary group is a totally real subgroup of real ends. So monodromy is a totally real. So anyway, so this has a infinite section which is defined everywhere. Now point is that I'll construct that this is like a lengthy process. I'll construct a algebraic section of it over the complement of the theta divisor. That's one of the points. I'll try to describe the construction. It's purely algebraic geometry, but like take any E in M minus S.
Recall that S is the subspace of M where H naught of E tensor tau is 0. So now, yeah, yes, I was trying to mention it, and here complement is absent. So now, I'll now write down an exact sequence. On X, some notation, I'll take consider X cross X. There are two projections, I'll call them P1 and P2, and it has a diagonal. The reduced diagonal. Okay, so now 0 going to P1 of a star E tensor tau. I'm taking E in this. So I pointed out, it was pointed out, this is 0. And I mentioned that Euler characteristic of E tensor is 0. So H naught of E is 0 if and only if H1 is 0. H naught of E tensor tau is 0 is same as H1 and E tensor tau is 0 because Euler characteristic of E tensor tau is 0 by the Riemann roch formula. So therefore, this bundle has 0 cohomology. There is no cohomology. 0. E tensor tau. And that E to upper star E tensor tau. Tensor. I'll write the same thing. We are not. Oh, I should have not. I should not have reviewed this. Sorry, E star term. E tensor tau is star term. Delta. Now I am tensoring with delta. So the quotient is supported on the delta. Let us look what is the support of delta. Support of delta, E will come. First of all, let us recall that I can identify delta with X by the any of the two projections. It doesn't matter. So I'll identify the delta with X by the projection P1 or P2. So this is O tensor delta. So the quotient will be this restriction to the delta. So now what is this restriction to the delta? Here it comes E on X. Here it comes E star on X. And in tau is tau on X and tau on X. Tau on X is K to the K because the tau square is K. So these two tau will together will give K. So this will give E, this will give E star, and these two together, tau together will give me a Kx. And what is the restriction of OX cross X to the delta? It is by the Poincare exemption formula. It is the normal bundle of the delta, and the normal bundle of the delta is identified with the tangent bundle of the X by either of the projection. If it's P1 and P2, we see that the normal bundle is the same as the identification of delta with X gives the normal bundle of X, delta to the tangent bundle of X. So it becomes Px. So only thing is survive E tensor is the ND. This is supported on delta. So this is on X and delta, which is same as X, ND. Okay, now let us look at this. By Kuneth formula, cohomology of this will be cohomology of this, but all cohomology of this 0. So all cohomology will be 0. And just one remark that this bundle is like not arbitrary, because if it is here, then this also is here by shared duality, because H1 of E star tensor tau is H naught of dual E, then tau star tensor Kx. But Kx is twice tau star square, so it becomes H naught of E tensor tau, which is 0. So if E is outside, E is on this M, so I'm saying that all I'm saying is star is also in. This implies star also is in. So it's also cohomological, all cohomology families, but we don't need it. That one of them is 0, so that means this tensor product has by Punnett formula, all cohomology is 0. So I'm not writing the everything. So now we'll look at the long exact sequence of cohomologies. Recall H0, 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 then H1. H0 is 0, H1 is 0. So H0 to H0 is an isomorphism. So H0 of P1 of a star of E tensor tau, tensor P2 of a star, E tensor E star tensor tau, then the O X cross X delta is same as H0 of X and G. This is delta X supporting delta. Now, these are the canonical section given by the identity morphism. So I will look at this section given by which correspond to the identity morphism. So there are unique sections which restrict to the identity morphism on the diagonal. Unique section because equality. So I'm picking out of that section. So what is after we call the, because I don't want to mess up with the notation. Beta. So beta is the element here which corresponds to identity automorphism of by this isomorphism. So now I'll restrict beta to twice the diagonal. This is an interest. So now, so this is a section of P1 of a star of E, tensor P2 of a star of E, restricted to 2 delta. I'm restricting everything to the 2 delta. And tau tensor. Sorry, P1 of a star tau. Tensor P2 of a star tau. But I'm separating it out. I'm just writing it differently. The same thing I'm writing it differently. I am taking the E and E star together and tau star together. But I'm writing the same. P2 of a star tau. Now the basic standard fact is that P1 of a star tau, it's a P2 of a star tau. Tensor O X cross X delta. When I restrict this to 2 delta, it has a canonical section. It is even determined by the property that these are the canonical section. Determine the property, the following property. Restriction to the diagonal is 1. Makes sense because the diagonal makes sense 1 because tau and tau, if we restrict the diagonal, it becomes T tensor T becomes K, and O delta restricted to diagonal becomes the normal bundle of point adjacent, which is same as the tangent bundle of the curve. So T tensor K will become O. So there is one small catch is that you identify the normal normal bundle with the tangent bundle, right? But if you tangent bundle, you can identify using the projection P1 and you can using identifying the projection P2. These two differ by a sign. So now statement is that standard statement is that there is a unique section of this on which restriction to the diagonal is 1 and the involution, this is invariant and will be xy going to yx, not exponent, not curve, only point, alpha beta going to beta alpha. If this line bundle is invariant under that involution, and 2 delta is is preserved by that involution. That involution acts by multiplication by -1. There is a unique section of that. There exists unique section of this. I'm not writing this. Let us call it whose restriction to the delta is 1 and that the involution acts as multiplication by 1. I have chosen an ordering. It's express and chosen an ordering. That's why it's at 1 and involution acts as multiplication by. So now you see these are the section on 2 delta. Canonical section, canonical trivialization on 2 delta. So, but on beta is a section of this. So I get a section of this, right? So there exists, I mean, this part becomes trivial, right? By this observation. So I get a section of this. So the statement is that there exists unique section beta prime of H naught of 2 delta P1 upper star of E tensor P2 upper star of E star has that beta restricted to 2 delta, that section is this beta prime, I'm saying the unique claim, tensored with this section. Let us call it gamma. Unit section gamma. Right? We have constructed a beta here, and we have constructed gamma here, so there is a unique beta prime which has a disequality hold. Now look at this section beta prime. What happens if you restrict to the diagonal? Recall how beta was behaving at the restriction to the diagonal. It was identity. The restriction of beta prime to the diagonal is identity of it. So now by Gaussian construction, beta prime is a connection, holomorphic connection. So how let's recall how he describes the connection. So how such a trivialization, how such a section defines the connection on it. So Gaussian construction connection, I think it's called Gaussian. I don't know anything. Literature is called Gaussian construction. Any section of this whose restriction to the diagonal is identity is a connection, is a holomorphic connection on it. And the section gives a connection as follows. How this beta prime will give a connection? So S, take a section, a locally defined section of S to beta prime, P2 upper star S. See, S is a section of beta is a section, beta prime is E and E star, right? And so I can X is a section of E, so I can contract that, and so on. I get a section of minus your this vanishes on the diagonal, so it defines this is a section, locally defined section of E, and this is a locally defined section of E star E tensor. And you can say that this satisfies the Leibniz identity, so this operation will give a connection. Okay, so now I think I'll try to wrap up. So this is sorry. So I construct a holomorphic connection, algebraic connection only. So now this is M is a moduli space and a moduli space of connection on M minus S. CE. No, what is CM. moduli space of connections. On M minus S, I have produced a construction. Given any E, by this process, we have constructed a holomorphic connection. This is actually algebraic construction. You can use the algebraic of this bundle by this construction. So now let us recall quickly again what we have done. So first one we had is just con theta on M. So it has a Boolean section, which is infinity section, and con theta M minus S to M minus S. There is the algebraic section given by the theorem differential because it's trivial bundle, so it has a trivial. Now, on the other hand, we have the Cm over M, which have the C infinity section given by the non-Seshadri section, and Cm over M, M minus S, restricted to M minus S, section given by this first section. What is the notation for the first? Let's call it psi. So this you have done, right? These two are holomorphic section and these two are algebraic. So now, what happens when I give a section of a torsion? Con theta over M minus S, M minus S. Since it's a T star M torsion, I'm giving a section, it gets identified with T star M minus. Right? Because I have a section, this gets identified with a section because any element, what is the map? Take element W here, project it here, call it a Q. I'm just temporarily putting a notation Q. Take any W here, project it to Q, then apply this section. What was the section? Just called T. Apply T. You have come here. Apply T, T plus. T plus Q at, sorry, T plus, sorry. Q goes to T plus Q. Maybe that is more or less. I mean, you have to base what the same base point, same point here. I was trying to figure out. Like this. It goes to fiber to fiber. Anyway, so this is an isomorphism. So on the other hand, this is an also this is an algebraic section. Sorry, this is an algebraic section this side. So this is identified with same way Cm over M minus S over M minus S. So these are. So what is the consequence? I am getting a map from five. Let's call it fun. So I have got an isomorphism on this or this over the M minus S because both are identified with this. Now theorem. Phi extends. No, this is then algebraic now because this is algebraic, so composition. Phi extends to an isomorphism. Con theta Cm over entire. So this isomorphism. I should theorem 2. So let us call extend. Let us call phi tilde extended isomorphism. So now I got theorem 2 is that phi tilde takes the equivalent section to the non-same section. So Q composed with phi tilde is not NS. So the Nurseman has this connection on. So see, this is one is the connection on the bundle. They came from the bundle on E, and another came from the theta bundle connection on the theta bundle. So, but the statement is that this section, this algebraic section takes this infinity section to this algebraic isomorphism takes this infinity section to this infinity section. Now, I think I mean one, two. Huh? Okay. People may not be happy with it if I extend. Anyway, so now some more properties of this isomorphism. No. You can say that, but it is a catch there is that for example, equivalent construction is highly non. It is not a one cannot claim that you have a very simpler construction. Different one you can say, but you cannot say claim simpler construction. Because equivalent theorem is highly absolutely non-trivial. Functional application, yeah. Very dense paper. Yeah. Okay. I wanted just a few seconds. So. Utility, we can compute the differential of the Nord-Simon Seshadri section, etc. Yeah. So let me not. You just wanted to say something. I wanted to say that this has a natural symplectic structure. First of all, CM has a natural symplectic structure because it is given by H1 of the local system, and the local system is endomorphism valued, and there is a natural pairing. So this is a natural symplectic structure. Holomorph algebraic symplectic structure. This is a natural symplectic algebraic structure because from theta over M, and theta is a line bundle on this, right? The point is that this sheaf of connections has the property that quote unquote sheaf, it is not a sheaf again, let me say. When you pull it back, it has a tautological connection. Pi upper star of theta has a tautological connection, has a tautological, absolutely tautological, because splitting, pullback of splitting, etc. That's the tautological algebraic connection. And that it's only a connection you can talk about curvature, and curvature becomes symplectic form. The curvature of the tautological connection is symplectic form, and this has a connection given by the pairing representation. So the third statement is that this isomorphism is a symplectic structure. So I'll end with a just natural question. This from Simpson's law, this M. Character variety or the modular space of connections or is just same. So this has a natural hypercolor structure. This is from Normal Hus theory gives a natural hypercolor structure. So now look at this isomorphism. This completely canonical isomorphism. By looking at without looking at this, can you see a hypercolor structure here? That's a natural question. I'll stop here. Thank you for your attention. No, hypercolor, no, that is Calabi-Yau. Hypercolor is complex event dimensional. There's a IJKC complex structure, quaternion structure.
In that case, it is and
Thank you. Thank you. Sorry. These tricks with the diagonal and that thing. There are such tricks also in this paper which I wrote long ago on the diagonal varieties where the diagonal has.
So, good afternoon. It's a pleasure to introduce Professor Claire Vosha from Jesu, Paris. She will speak on universally defined set.
Thank you for the invitation to speak. I am sorry I have not been able to travel to India this week. For a while I did not meet Kapil, but I have a great memory of his visits in Paris. That was probably maybe 15 or 20 years ago. At that time, we had a very good system of visiting, exchanging visitors between France and India. Especially that was organized by, I think, Le Potier and also Meta. And Kapil went to Paris within this exchanges. And so I have a very good memory of all of our discussions, and I am not the only one because I was discussing with Christian Peskin last week, and he remembered also very well the Kapil's visits in Paris. So let me explain. So the subject of my talk, in some sense, it's very basic and elementary, and I hope to convey what is done and the motivation, and also what remains to do. So I will work on field K. Probably I am not exactly sure of what are the needed assumptions, but at least the field K maybe should not be finite. So maybe say of characteristic 0 probably not necessary. Infinite maybe enough. And so if you have X, which is a smooth variety over K, so you have the Chow groups CHI of X. So I index the cycles by the codimension. And the importance of smoothness here is that I insist on the functorialities we have. If you have a morphism, between smooth varieties defined over K. In fact, it's only X smooth that is important. Then there is a pullback. So it's essential functoriality, phi upper star from CHI of X to CHI of Y. And furthermore, so that's the important, the main thing that I will be using. Furthermore, there is an intersection product. And so these two things that justify why I want to work with smooth varieties. And so now let me explain what I call universally defined cycles. So now I fix a dimension D and fix the degree of the cycle, so the codimension. Okay. Then the definition. So a universally defined cycle of codimension I on four smooth varieties of dimension I, sorry, dimension D, everything over K is the following data. For each time I give me a smooth morphism of relative codimension D with Bx smooth. Okay, so this is a family of smooth algebraic varieties of dimension D parameterized by a smooth base. Then, associated to this, I have a cycle that I will denote by Z. So the cycle should depend on the morphism and not only on script X. So, okay. So, and of course, I want that this data satisfies the following two axioms. First of all, of course, when you have a smooth morphism, you can restrict to Zariski open set. So, so this is okay. So it's also a sort of a locality or localization axiom. Then you have the condition that Z of phi u is just Z of phi restricted to u. And the second axiom is a base change axiom. We want to say that really what is important is what is it's the data concerns the fibers, and so so now you consider a family over B, and now you make a base change. Of course, I want that B prime is also smooth. Then, of course, you can make the fiber product, X prime over B prime, which will map to X. Okay, so this is R tilde, and you want in this situation. Is there a question? In this situation, you want that Z of, so call it phi here, phi prime, then Z of phi prime is R tilde upper star of Z of phi. And this equality, of course, will be, so this is this equality is in CHI of U, and here this equality will be in CHI of X prime. Okay, so this is a definition, and it will be immediately justified by one example and and one theorem, and only maybe later on I will explain my motivation to study this. So example. It will be the main example, and finally that will be the only example in some sense. Example. So of course, when you have if you have a smooth morphism, then you have the relative tangent bundle. And so you can consider the Chern classes, the Chow-theoretic Chern classes for the relative tangent bundle. And also, of course, you can consider polynomials in the sense of the intersection product, polynomials in the Chern classes. And so, and the point that they are universally defined for the simple reason that you know these axioms 1 and 2, they are satisfied by the relative tangent bundle itself. Here, that will not be in the Chow group, but really as vector bundles. The localization axiom, this is just saying that the relative tangent bundle of phi u is the restriction of the relative tangent bundle of phi, so it's obvious. And also the relative tangent bundle, it is a functorial under base change, so that works very well. One and two are the analogs of but for vector bundles. And so, in fact, the main theorem is that. So there is a small caveat, but basically the main theorem will say that they are the only ones, giving a sort of universal characterization of the Chern classes. So it's slightly less than I just said. So let Z be a universally defined cycle of codimension I on varieties, smooth varieties of dimension D. And I assume that, in fact, the result will concern cycles, I mean, the value of the cycles on the generic fiber. So in case, I can certainly assume this condition. Because the generic fiber has a dimension D. Then there exists a unique polynomial P of x1 xd of weighted degree I. Of course, in these variables, x1 to xd with degree of xg equal to g. such that, and this is such that for any variety x over x over a field. Okay, like I am considering really the fibers. So where L will be a field containing K. The cycle Z of X is P of C1 of X. So then, well, maybe it's yes, well, in that case, it's just, I mean, I am just considering a variety over a field, maybe a subfield of K, maybe K is itself, and I'll consider really now the value of the cycle on the fibers. So rather, in particular, at the generic point, rather than the whole thing. This equality is in CHI of X. So there is a small deception concerning the conclusion, because on would prefer to say there exists a unique polynomial P like that, such that simply we have the equality. So we would prefer this. So Z of phi. But I was simply not able to prove this. And as I will show you, it's absolutely not obvious. I am saying I have a universally defined cycle. Its value on fibers is computed in this way. And this question, it is asking whether there could be a contribution from the base, and that I was not able to solve this, to answer this. So the statement is this one, that I know only what is the value of the cycles on the fibers, closed or generic. Okay, so in fact, it is interesting to compare this statement with the Francetta conjecture, because it's very, in some sense, the Francetta conjecture for curves, the Francetta conjecture is not a conjecture, it is a theorem. So what does it say? It says that it says the following: I consider choose G, say G at least 2. Consider the universal curve CG over MG. It does not exist, but in fact it will exist over Zariski open set of free automorphism curves. Then of course, you consider the generic fiber of this. So the Francetta conjecture, it is not saying what is the Picard group of this universal curve. It is saying what is the Picard group of this universal curve at the generic point. And the Francetta statement. So there are a number of people there are different proofs of this Francetta conjecture. So, Mestrano was one of the contributors, but there are other ones, and maybe also Hauer. This is saying that peak CG is Z times the canonical class. which is exactly related. The canonical class, this is the C1. And you see the statement that takes exactly the same form that a priori we maybe have a family, so it would be nice to know the Picard group of the total space, but it's not what we do. We just say the Picard group of the generic fiber is of this form. So you see even in the statement of the Francetta conjecture, there is this conclusion, which is only for, if you like, for constant morphisms or morphism to a point or varieties of defined over fields and not families. So a priori, so from that viewpoint, the two statements are very similar, but there is also, on the other hand, there is a big difference. Is that in fact for universally defined cycles, so what says my results? We'll say that if you have so that will be, so now that will be for co-dimension one cycles on one-dimensional varieties. My result will say that given such a universally defined cycle, there exists a number such that for any curve C over a field L containing K, Z of C is lambda C1 of Kc. And the point is that I have a statement which works for all genera. So okay. So this is in this sense that the nature of the statement is slightly different, and I can explain very well why this will be the same lambda. It is simply the key point. The key point of this definition. The key point of of the definition I made here, that you see, I consider smooth morphism of a relative. So I didn't say no. Relative. It's not co-dimension. It's a relative dimension. So the key point is that when I write these axioms, the data I start with are these smooth morphisms of relative dimension D. But at no point I put a properness condition. So, and then this is very nice because what I can do, very nice for me, I like it. What I can do is that I consider mg, then I have this, so this mg bar where I add, say for example, one nodal curve, one nodal curve, and then of course then the fibers here they will have singularities, but because so basically so do this. Here I will have this, but because I don't worry about properness, I just remove this fiber, remove the critical locus. Okay, I just remove the singular the point where a fiber is not a smooth morphism, so that means that I remove the knots. Okay, and this gives me a smooth family. And to this smooth family, I can apply my base change axiom. This is the point is that over the boundary, what I will get is a curve of genus C G minus 1 minus 2 points. And so that means that with these axioms, I can see at the same time curves of genus G, G minus 1, etc., up to the price of removing points. But in fact, removing points, it's not a serious issue. So that's why this definition finally lead to a slightly different statement with this multiple of the canonical class appearing to be the same multiple for all genera. Okay, so that was the point I wanted to make, the relationship with the Francetta conjecture. And now I will explain, I am going to explain basically how the proof works. And then after that, I will explain my generalization and my motivation for doing this. Okay, so are there any questions? So about the proof. So I start with any smooth x of dimension d. Say over a field, because you see the conclusion is over a field. So let so n large. So I consider the Grassmannian of d-dimensional subvector spaces of my k to the n. So maybe not the same field. Well, I can take k here. Okay, and I observe that because n is large enough, I can find maybe depending on d, I can find an embedding of x into g of dn. Okay, and now also what I can do, I observe that if I choose sufficiently ample line bundle L on GDN. So L will be a high degree multiple of the flicker polarization. Then the ideal sheaf of X twisted by L is generated by section. Sections, and so by Bertini. Yeah, I think maybe Bertini. I'm not sure it is used. Yeah. Okay. So it follows that there exists a complete intersection say y contained in G of dn, which is of elements of in this linear system, and more precisely those which contain x, with a dimension of y equal d, and x contained in y as an irreducible component. Okay. So the conclusion is that any x of dimension d is an irreducible component of a complete intersection in a Grassmannian. I could put projective space, but Grassmannian is important here because the Grassmannian, it contains the Chern classes, so it contains many more classes than the projective space. Okay, but of course, y is singular in general along hypersurface in X, namely okay, so this is the intersection. D is the intersection of X with the complement of the residual component of y. So if you do y minus x, so there is a remaining variety which is called the residual component, and of course along this intersection, y will look like this, x, and here we have this d, and here we have the rest. I won't care about the rest, and the y is here. Okay, and now the point is that this d is not any. The d, we know very well what it is. D is a determinantal hypersurface. Namely, you do this. So let me. So yeah. So you have our. So we have a certain number m, which is the dimension of. This is a codimension. Sorry. This is the codimension of x in the Grassmannian. So y is defined by m equations that all vanish along x, and that gives me something like this. So let's say that we are over k. So these equations, they can be so they have a differential along x. So that gives me, so if I do this for all these equations, that will give me something like this, Ox to the m, and this goes to, now I have to consider the normal, I think this is this nx over g dm dual, because I differentiate the equation, and of course this is twisted by L. Because of course the equations are not functions but sections of a line bundle. So you have a certain morphism. It's a differential mix of evaluation and differential differentiation of these equations. So we have this morphism. They are both of rank m, and my d is defined by the determinant of this differential. But in fact, I observe that L being very sufficiently ample enough, this morphism is a generic. Okay, and so now there is the following point that is important. Of course, so let me explain what I want to do. The conclusion of this is that x minus d is contained in the smooth locus of a complete intersection in GDN. No, yes. Smooth locus of Y, and Y is a complete intersection. So I am going to compute my classes for the smooth complete intersections and then restrict to X. Now I have a problem because, of course, so I apply my axiom, my universally defined cycle, which is here. It will restrict to its value for X minus Z, so it's good. But the problem is that this one, I lose, of course, normally I lose information. So this restriction is not injective in general. So the key point is a lemma which says that universally it is in, this morphism, this restriction morphism is injective. And so more precisely, what is the lemma? Which means the following: I consider all these morphisms. So that will be on. You have to consider something like this. Let B to be. You see, I have to choose these M equations. So Ix of n. Okay. Or I could directly replace because maybe maybe I could. It's much more general. I could. Okay. M. This is exactly the situation that I have here. M sections of this twisted normal bundle. Then over I can consider over this B. So now that over B cross X, there is a universal morphism, namely O B cross X to the M with value in NX. Yeah, NX over D. Okay. There must be something. Oh, yes, but I think this one is not. This is not this one that I have to put here. It's the sub. I should use a gum, but I am afraid that will be. This is dangerous. So sorry, I prefer not do that. So I replace my OX to the M over the Grassmannian. It becomes the universal subshift of the Grassmannian. So I have this universal morphism, which is just the universal version of this evaluation morphism. And of course, there is now a universal hypersurface like this, which is in B cross G of M Ix of so this vector space here, which is the determinantal hypersurface associated to this universal evaluation morphism. And of course, I need the X. No, that should not be this. Sorry. Okay, so sorry for the. And now the lemma, which is in fact not very hard, is that if you do the composition chi of x to, so now we say pull back to chi of b cross x, and now you restrict to chi of b cross x minus this universal determinantal hypersurface, the result here is injective. Okay, and then how is it used? This is very nice because this is already telling me that universal defined cycle will be determined by its value on the complete intersections in G of dn. Why? Because I do as before. I have this. I have take the same B. So now let's do rather B, which is the Grassmannian parameterizing n m. Sorry, G of m equations in L containing x, vanishing on x. Okay. So as I explained, so what we have is x cross b minus d. It is so of course this so now this b, it is contained in G of m h0 of J. Okay, this Grassmannian essentially it will parameterize the complete intersection in the Grassmannian. But the point, so over this Grassmannian here, I can consider the universal complete intersection. Okay, so in GDN, so each time I give me m equations that produce a complete intersection, which might not be a complete intersection, but what I so in case I define something, so this is contained in B cross. Okay. Now the point is that this morphism here, it is very bad because there are singular fibers, that are not of the right dimension, but I simply consider the open set where I actually have a smooth complete intersection of dimension D. And the point is that what I explained is that the x cross b minus this determinantal hypersurface, it is contained in this I0 as a component. So everything is over the same B. So now I apply the axioms 1 and 2. And conclude that, of course, this universal smooth complete intersection, it has this phi 0, which is here. This phi 0, it has, so I start from an x, and so I have a certain z of phi 0. My axioms, so So you see, if I use the two axioms, I get that Z of phi 0 restricted to this this thing here, x cross b minus d. It must be by now I apply again the base change axiom and the localization axiom. It must be the pullback here 1 upper star of z of x restricted to x cross b minus d. So and this is saying now if the lemma tells that this determines z of x because the pullback followed by a restriction map of complement of the universal determinantal hypersurface is injective, and so the conclusion that the knowledge of z of phi 0 determines z of x. So this is one step, and the second step, and I am not going to enter into this, is to compute z of phi 0, which is I mean, obviously much easier with some well, no, there is a point, but okay, and then prove essentially prove that this z basically that it is a polynomial in the relative Chern classes of phi 0. Okay, so that is the strategy of the proof. And so, okay, so what I would like to do is to explain my motivation and to explain a conjecture. So this notion of a universally defined cycle, it can be so there are several generalizations, but originally I wanted to study of now not universally defined cycles on smooth varieties of dimension d, but on powers. So now a fixed k on powers xk of smooth varieties of dimension d. Why this? So the definition is exactly as before, same axioms, except that everywhere you replace x by x over k. So let's go back to the definition. The definition it is here. The definition is here. Now I start with the same data, x over b, smooth morphism of relative dimension d. I will simply consider morphisms which are now in CHI of x to the k, I mean the relative case power. And then everywhere put k over b and have the same axioms. That will be now, of course, I mean, everything you will have, you will replace your original family by its relative case power. Okay, so same axiom, etc. And now, if you do this, you observe that now there are, in that case, there are extra universally defined cycles coming from the diagonals. diagonals, that is, of course, usually the diagonals, they are indexed by, you choose a partition I equal I1 to IL, a partition of 1K. And then you, for each, of course, for each morphism like this, you will get a relative diagonal indexed by this partition. Okay. And this relative diagonal, it is by definition, it is theoretically it is the x1 xk over a given b with the property that xi equal xg if both indexes I and g belongs to some I r for some r. Okay, so this is the way we describe the various diagonals. And these diagonals, well, they have a certain codimension, and the conclusion is that so maybe it's better to, well, the diagonal like that, it is isomorphic to x to the L over b. Okay, you just, because you have all these equalities, so finally you have, in a diagonal, you have only L distinct points, so it is isomorphic to this relative power, and of course there is an inclusion morphism like this, which I call delta I. And obviously, so that gives me the classes of these diagonals, and they give me extra universally defined cycles. But more generally, we can use these diagonal morphisms to, I can use these relative inclusions to push forward universally defined cycles. So we get plenty of universally defined cycles on these pools of d-dimensional varieties, which are of the form namely so sigma over I of delta I push forward of universally defined cycles, which are of the form pi. And here I have to put a polynomial. So here I am on here, so I have the values p r g upper star c c l. Okay, so I have for each factor will contribute with a relative chain class, and I can pull back them via the various projections like this. So finally, that gives me a large number of variables, and I apply a polynomial to this. And of course, I want that the pi should be of weighted degree, of course, again, g in each variable. So sorry, weighted degree of a certain weighted degree, where where each variable PRG upper star CL has so No, it's more from, well, so let me not say anything about the degree. Well, in any case, you can compute the codimension of this cycle, so it's more complicated. So let me remove this discussion of the degree. So in any case, we have a universally defined cycles on powers that takes this form. So conjecture. All universally defined cycles on case powers are given again on fibers. That is when I go to generic fiber or fibers over spectrum of fields. By are given on fibers by such formula. More precisely, yes, if I have a Z, then there exists the universally defined cycle on case power, then there exists a unique collection of PI determined by Z, such that my Z is given by this formula, at least on fibers. What are the results? That uniqueness is okay. Motivation. The motivation is enormous because it comes from the study of the case where D is equal to 2, and you consider we want to study the geometry of the second of the punctual Hilbert scheme of surfaces. So this the Chow groups of xk and the cohomology of xk are very interesting objects. So the relationship between cohomology and Chow groups, it appears in, for example, well, in a conjecture made by Boville and myself about the case where X is a K3 surface. And the point is that due to work of Descartes, so I should mention many names, for example, Nakajima, Lane, Ellingsrud, Gutsche, Lane, of course, Gutsche here, etc. So there have been plenty of work, very important ones, and in particular about understanding the Chern classes of these varieties. Now there is a work of De Cataldo and Mignorini. They observe that when you have so they do not introduce this correspondence, but you can use all these correspondences. They also appear in the, of course, in the work of Nakajima. So X maybe is a smooth surface, and you have for each I, you have a certain correspondence gamma I to S. So I is I1 to IL. You you have a correspondence like this. This is a partition of 1K. How we obtain this correspondence is simply that you use a diagonal inclusion of SL into SK, and then here I am going to symmetrize this correspondence, and here you have the Hilbert homomorphism. Over this diagonal, the fibers are of a certain dimension that we know very well. And if you do this more or less this thing, then you get here a certain correspondence. Okay, and this is what I call the Cataldo-Mignorini correspondence. And what said the Cataldo and Mignorini is that you have all these the collection of all the gamma I per star. It injects the Chow groups of sorry, this should be X. It injects the Chow groups of the Hilbert scheme in the direction of all these Chow groups. But the key point is that in this here we have the many interesting classes, namely we have the Chern classes of this variety. We have the so-called strata, namely the strata, basically the strata, they come from typically over the diagonals. You have a strata, but you can also refine the strata by analyzing the structure of point in the fiber. So and there are natural that shows that the Hilbert scheme contains plenty of natural classes. But the point is that when you apply this De Cataldo-Mignorini correspondence, so you can, of course, you can consider polynomial into these classes. You apply this, and now you are here, and what you get are now they are universally defined. So the point of this whole project was to get simply by the theory of universally defined cycles, many results, in particular a splendid result by Illingsrud, Deutsche, and Lin, saying that typically if you consider simply the top Chern classes and consider their degree, that will give you the so-called Chern numbers of the Hilbert scheme that determines the complex cobordism class of the Hilbert scheme. They say that this can be computed as polynomials in the Chern numbers of the original surface, assumed to be projective. And that result, which is rather, I mean, is a very beautiful result, but their method is a bit painful, and that will be an immediate, immediate consequence of that conjecture. But I have also many other applications in mind. So I'm sorry, maybe it was too long. I should stop here.
Hello.
So let's see. Just unmute. Okay.
Yeah. Hello, can you hear me?
Yes, yes.
Yeah. So I have two questions. One is, what about other cohomologies than intersection cohomology? And the second question is, suppose you add a very ample relative line bundle to X over B, and then you can take the embedding and put a Kähler metric, and then take the Stiefel-Whitney classes of the resulting metric on the tangent bundle, and therefore have something in even and odd mod 2 cohomology. These will be universal for X over B with a very ample chosen line bundle. So will they generate what will be other universal classes? So first question was about all other cohomologies, and second, a specific question about this.
I try to understand. So the first question is whether there is a cohomological version of the result, because the result is about Chow groups. Are you asking whether in the whole definition, statements, etc., I could replace Chow groups by cohomology? Is this the point of your first question?
Higher Chow groups or Eliadic or whatever, singular. That is one question. And the second question is, instead of pairs X over B, I add a very ample line bundle relatively.
No, I understand.
On X over B.
No. The first question, I didn't understand what you want. So do you want to make the fibers singular or the total space singular? I did not understand.
Oh, it's not working. I can't hear what I can't understand. And what about my specific question about relatively very ample? You can't.
Hi, Claire. I had a question.
Yeah.
So if you look at the Kunet components of the diagonal, one would imagine that they should also be universally defined somehow.
No.
So there seems to be some contradiction.
This is a very nice question, and I thought about it because I was afraid I am making a mistake, but because of this conjecture. But the point, if you think, to have you need the Kunet decomposition. It is absolutely not well defined in families, in the sense, yeah, how to say. The key point to have the Kunet decomposition is properness. So if you have a proper family, and maybe you also need a polarization, then I think then you get the Kunet decomposition. You know, the Kunet decomposition is the point is that it is not defined in family unless you add extra. You know, it's like in the decomposition theorem of Deligne. You know, the decomposition theorem of Deligne or Deligne-Blanchard, when you have a morphism, and you need a projective or Kähler morphism, compact Kähler, proper Kähler morphism, it decomposes the push forward of cohomology into direct sum, so in the derived category. This decomposition is not canonical. It depends on a relative polarization, and this is exactly the same for. And in fact, you can deduce this decomposition theorem from the existence of a relative Kunet decomposition. But the problem is that this relative QNet decomposition is not it depends on the choice of a polarization. So no, that will totally contradict my conjecture. The QNet the QNet components of the diagonal, they do not provide universally defined cycles, unless you and even because really what you need is a polarization plus properness. So there is no I mean, it's not a way to produce universally defined cycles. So no, this does not provide a further universally defined cycles.
There is one this characteristic.
Now it's better.
Is it because of this?
Yeah, that's okay. Thanks, Claire. That was a wonderful talk.
Yes,
Thank you.
yes, sir.
I think now we are
Thank
going for.
you. Thank you very much.
Yes, sir. Yes, online talk around.
When is the next talk?
You can check on the thank you very much.
When is the next talk?
When is the next?
Yeah, we can hear you.
In half an hour.
Half an hour.
After
Okay.
half an hour.
Yeah, the session is over, so we're closing. Thanks
Okay.
for joining.
Makes sense.
Thanks a lot. We'll end the meeting.
Thank you.
Thank you very much for the nice talk. Welcome back. So it's my pleasure to introduce Professor Krishna Hanumantu from CMI. He will speak on.
Course, I remember many things from the course that he was talking about something very deep, and I was not understanding any of it. So, from the course. So, it was very, I could sense that, but I was not getting it. So, it was very nice to interact with him over the years, and I'm very happy to speak in his conference, and I wish him all the best for future. So, I'm going to speak about Seshadri constants. Let me start with the basic setup. I understand the audience is somewhat diverse here, so I'll try to introduce the main ideas behind them. So I'm going to. So for a little bit, we'll work with arbitrary fields, algebraically closed, but very soon we'll stick to characteristic 0. I want to start with a theorem that Seshadri proved. This is in the late 60s, early 70s. This is the beginning of this whole story. So this is what is called Seshadri criterion. So something Seshadri used in some constructional moduli, a lemma he called it, was written down by Hartshorne in his notes. And then this led to some, this is like not the main thing that Seshadri did, of course. No one talks about this as this one of the main contributions of Seshadri. Yet this turned out to have such an impact that, a lot of people work on this, especially in the last 40 years. So what does this criterion say? So if L is a line bundle on X of this kind, so it says something about ampleness. So when L is ample, there is a positive epsilon such that so we have the intersection number of L and what C for all curves. You can just and for all X. Okay. So this is you want L dot C to be bigger than 0, of course. That's a necessary condition for ampleness, but that's not sufficient for ampleness. However, if you insist that L dot C is not just positive but bigger than a global constant, it turns out that other properties are naturally consequences of this. So I want to give a quick sketch of this proof because this is in some sense not only is this result the origin of the subject, but the proof itself is crucial to the study of Seshadri constants. So, and the proof actually is not very complicated. It's just more or less a direct application of Markov-Marchesjan. But you have to do a little trick which sets up the whole subject. So what is this? So one direction is the easy one. So assume L is ample. Okay, so assume that L is ample. You want to show that L dot C is bigger than something like this. So here the point is so if L is ample, we know that some multiple is very anti-positive K. So we can embed in some projective space using the ample derivative there. Then we take a curve here on the point. Let's look at KL dot C. KL dot C is actually nothing but the degree of C embedded in the projective space. And we know that degree is always at least a multiplicity. Inside a projective space, degree is of course always bigger than multiplicity is the measure of singularity. So it's locally this polynomial, the degree of a polynomial, which is the largest degree term, multiplicity is the smallest degree term. So there is always greater than equal to 0. And if you look at the inequality, so we have K dot so C dot L is greater than 1 over K, and K is something that L determines. It does not depend on C or X. So this is the easy direction. So if you have an example, then you have this epsilon, you simply take it to be 1 over K. The other direction is the more interesting one. So I'll keep this condition, but erase this. Okay, so now, so we have to assume that there is an epsilon of this kind. We want to show that L is ample. So we use this. Now, condition says that L is ample. Substance of X, including X itself. We want that condition. So the hypothesis guarantees that for curves we have the condition. Is positively wrong, but it's even better than some epsilon times multiplicity. And by induction, we can show that it suffices to show So you can show that L power n is positive, then it will, by induction you can show that for any proper subvariety this will follow. Okay, so now this is what we want. If L has this property, then L is certainly F. Because on every curve it is positive even. So if L is F, this is certainly true. Kleiman says this. Because the point is that we want it to be positive. If you simply assume that L is F, L power n can certainly be 0. But this condition will guarantee that it's positive. And this is the trick that I was talking about, where you do and show that something has non-negative self-intersection, but that implies that Ln is positive. So what is that trick? Simple tricks, doing nothing. So we're going to blow up the point. The exception divisor is E. Okay, so it's an integer. So the epsilon is given to you by the hypothesis. It's a positive number. I'm going to take an integer bigger than 1 over epsilon. And then what we want to do, I will go into the details here. This is the crucial idea. Look at the p dot of L, multiply by the integer and subtract the exception divisor. And it's an easy exercise to check that. To save time, I will not do this, but it's very easy because reference is a much easier condition to check. Just check it against all curves. You have some cases, if the curve is joined with the exceptional divisor, there's nothing to check because E dot C is 0 and L is ample. If the curve is completely inside the exceptional divisor, then this will have no intersection. But E dot C is actually negative because E is at 2n and restricted to the O minus 1. So again, it's positive. And if L into if the curve intersects C but not contain any, it's similarly easy to show. So if this is F, which is easy to check, Fn is greater than equal to 0. But that exactly implies that L power n is positive. Because this is the nth power of this is just an L power n minus 1. Okay, so it's something like this. So e to the n is negative 1 power n minus 1. And you have the positivity. Okay, so this is just a simple argument, but it turned out that this is an important idea. So nothing happened for about 30 years. Sorry, 20 years. It was, as I said, late 60s. I don't know the full history, but it was probably something that Seshadri has been telling people a lot. At the time, a lot of people knew this. I think that was in some paper of his in 70s. But people know this from late 60s. So that was that. But in 1990, so I wrote the criterion, but you will see where that will play a role. Then looking at something, I'll talk about what his motivation was. He was looking at Fujita conjecture. But he observed that these constants have an important implications. So x as above, and I'm going to take L and F. You will see why. F divisor I'll take, and small x is a point. He defined this number, which he called Seshadri constant. If the x is here, we'll just write epsilon Lx. This he defined to be reducible and reduced. So this is the epsilon that you have. So look at L dot C divided by multiplicity. It's certainly a non-negative number because this is non-negative by the hypothesis and this is a positive integer. So this infimum of some positive rational numbers. And certainly this is non-negative. And the Seshadri criterion can now be rephrased as n is ample. So this is what it says. Seshadri constants of Neff line bundles are non-negative real numbers, but ampleness is exactly when they are positive real numbers. One direction is easy, just like the proof of that theorem, but the other direction is what Seshadri criterion says. And I want to also give another equivalent definition. This is also an easy. There are several equivalent definitions. I'll write them today. So as you can see, blocks play an important role in this whole story. So either you compute the infimum on the variety itself, or you compute the supremum on the block. So here you do two. Okay, so P. Is, yeah, it will, I mean, it can be, so this is not clear, but at it will be positive. And it will be, it's an equivalent condition which occurs in equal part, but it can also be shown. This is equivalent. Yeah, so that's also true. These are all positive numbers, but also away from zero. Yeah, so this is also clear, like you were saying. Okay, so I should write it like this. Where is the so supremum of all positive real numbers F are ample. Okay, these two definitions is straightforward because to check something is F above, as we saw there, is just a matter of checking it against curves, which you can do by taking the image of that curve in X itself. So I'll forever, for the whole talk, I'll fix this. So this is my standard notation. So the Seshadri constant can be computed via this. It's sort of, it is a question about the Neff cone of the blower. So pi of x or L is Neff because L is Neff. But you can sometimes subtract with power in the direction of negative exceptional divisor. At some point, you will certainly be outside the Neff cone because E is negative. But we want to see where you exit the Neff cone. So the supremum is the supremum is achieved, it will be Neff but not ample, but the supremum is same whether you put Neff or ample here. Okay, so I will make a couple of remarks before we go into the motivation of the mind. So using these easy properties, using these definitions. So let's say L is ample, which I'll assume bounds. Epsilon is their real number, which is always positive if you assume L is ample, and it's not more than this number because of this property here. Epsilon is when this remains Neff. So the top self-intersection of this is non-negative, which will translate to the inequality that epsilon is less than epsilon power n is less than L power n. So epsilon is less than nth root of L power n. Okay, so this is clear. If value is very ample, epsilon is in fact even greater than 1 because the same trick that we had earlier of embedding X inside the projective space. Then Seshadri constant is a ratio where the top number is the degree of the curve and bottom number is the multiplicity. So that's at least 1. In fact, there is also two values globally generated and ample. It will not be very ample for this. And some easy examples. So if you take the projective space, so before I write that, note that this whole definition really makes sense only in dimension 2 or more. On curve, there's not much to do, and there's nothing to do really. So only one curve, and you take the degree of that curve, and which has to be positive. So Seshadri constants are meaningful for line bundles at least on surfaces or higher dimensional varieties. So the first example, so to speak, is this. So you take the O1 on P2. You know that Seshadri constant is at least 1 always for every very ample divisor. However, in P2 there is a line through on every point. So the ratio that you get is degree 1 multiplied to 1. So the minimum is 1. So epsilon is 1. And it's just fairly boring phenomenon. For every point it is 1 and there's nothing else to do. Whereas Seshadri constants in general have different values based on the point. So, but still this is the starting point. I just want to see what happens in the second description of the Seshadri constant. If you blow up P2 at one point, you have this two-dimensional Picard group here. And also this is H. H is the pullback of O1. And E is the exceptional divisor. This is telling you that H minus E is NF, because that's the supremum. And H minus E is somewhere here. So this is the NF cone of the blow up, which anyway you know, but it's just confirmation of that. So NF cone is span of these two rays, and this is the cone of curves. Mori cone as this. Okay. So before I give more examples, I want to talk about not only the other definitions of Seshadri constants. In fact, Vinay gives importance to another definition which I'm not talking about, which is in terms of separation of F jets. So he connects this definition to the property of L separating F jets where S is a natural number. So 0 jets, 1 jets, 2 jets. So this is a sort of separation properties of a line bundle. Separating 0 jets corresponds to global generation, 1 jet to very ampleness and so on. So I don't want to write the definition because it's not that relevant, but I must say that that is the original motivation for him. Using that, he is able to prove the following result. Okay, so in the paper in which he defines Seshadri constants, his main goal was to prove this theorem. Okay, so he proved that. Okay, so dimension of X is n, and now I am going to assume the field is complex numbers. So you have a complex projective variety of dimension n. L is an ample line bundle. So this is the setup. He proved that if epsilon is greater or equal to n over n plus 1, if this happens, then line bundles through Seshadri constants. And similarly, the other result was so the Seshadri constant is slightly bigger, even more bigger, that it's greater than this number for all x. This is very ample. So now these look completely arbitrary adjoint line bundles. Why are they important? They're important because of this conjecture, which is which is one of the important conjectures in linear series. So this is called beta conjecture. So X as above, L as above, by which I mean X is a non-singular projective variety of dimension n or complex numbers, L is ample. And he says that, this conjecture says that exactly the conclusions of Desmai's theorem. So this, as I told you, is an important conjecture in the subject. It's Riemann rock for n equal to 1. On curves, this is exactly what Riemann rock says, but n equal to 2 onwards, it's not real. But surfaces rider through this, it's a paper in ML, so it's one of the sort of important results in the subject. Now, n equal to 3, and I believe for 4 also, I have to, for sure 4 I was not able to check today, but 1 was proved by Ein and Lazarsfeld. The global generation statement. So it's open in other cases. Okay, so this is the motivation for Desmai. So he was thinking that possibly Seshadri constants might give a way to conclude Fujita type statements. So one needs to only show those bounds on Seshadri constants and you get Fujita conjecture. So this was his motivation. Obviously, I am writing this open in other cases. So this means clearly that the approach did not work, as I will explain now. So what he's hoping to do is not correct. The bounds on Seshadri constants are not correct. They are not as big as that theorem would like. There is certainly no converse to this. Yeah. This can be true with much less than this. Yeah. And also this is not true, as we will see. I will give 2 quick examples. To show that things can, Seshadri constants can be small, not like that, not big like that. So on a surface, for example, this would require us to say that Seshadri constant is at least 2/4 for every point. Then this would be globally generated. Sorry, 2/3. 2/3, yeah. Then K plus 3L is globally generated. So the question one can ask is Seshadri constant of any ample element on any surface at least 2/3? And it's not. Okay, so the first example is the following. So let's take a K3 surface. So, okay, so the K3 surfaces are extensively studied, a lot of results about them. One of those is that you take any even lattice with Picard number less than 11, a K3 surface, algebraic K3 surface with that intersection lattice. So you can always take a K3 surface with this Picard rank 2 K3 surface with this intersection matrix. So, and the Picard group of this will be generated by 2 curves. One will be the corresponding to these 2. So you have 2 curves like this. So this is in fact a rational curve, smooth rational curve, but this is an arithmetic genus 1 curve. So if you take the linear system associated to this E, I mean, standard calculations say that it's a pencil. So it will give you it's a base point free pencil. It gives a morphism to P1. And the fibers of this are elliptic curves, but I claim that there is a singular curve in the fiber. And that's a standard calculation using some topological characteristic, Euler characteristic, you can show that if every fiber is smooth, then the topological Euler characteristic of this will be the product of this and the fiber, which it is not. So this is standard. So this has a singular pencil, singular curve. Let's say E0. And standard calculations show that E0 must have double point, no higher multiplicity. So let's look at that. So this X in E0 such that multiplicity is 2. And if you take line bundle, which is gamma plus 3e, okay, so again, positivity of line bundles on K3 surfaces is studied extensively, and one can show that this is ample using some, within Mackay-Moshizan. So if you take epsilon of Lx, it's an infimum of certain ratios. One of those ratios will be this, because you can take any curve passing through that point. And L dot E0 is actually 1. Because remember, gamma dot E is 1, 0. Gamma dot E is 1. So using that, you see that it's less than half. So in particular, Seshadri constant is not more than 2/3. Yeah. Separately, it's known that this is in fact equal to 1/2. But for us, it suffices at this point to say that this is not correct. However, on the surface, we know that this result is true. So certainly, this is not a very fruitful approach for Fujita because the bounds are false. But things are even much worse. Here I am producing half. But Miranda gave a construction, which I will not describe because I don't have too much time. He says that for all positive delta, there exists X, L, and X. So X is a smooth ration surface. It's in fact a blow up of P2. Yeah. Yeah. Yeah, so it is base point free. Yeah, so it's not quite, the example is not that, it's not perfect. All I'm saying is that example shows that this can be less than this number. The conclusion is fine. The conclusion is defined in fact by Ryder, but it's more trivially true for this particular L. Yeah. So I'm just saying that this bound itself is not, it's not correct. You can't expect it. Yeah. And as Miranda showed, it's even worse. So for every positive delta, there is a triple like this, such that the epsilon is less than delta. So it's of course positive because L is ample, but you can make it as small as you would like. So Miranda constructed a blow up of suitably chosen points on P2 and alignment on it with arbitrarily small Seshadri constant. Basically, this goes for a toss. That's all I'm saying. This happened in a very brief period of time. 1990 was the paper. This example is 1993. At least it was in 1993 in a paper Fine and Lazarsfeld. And I don't know when the example actually was given. It must be soon after the Nice paper. So the point at this point I want to say is that the for this conjecture, for this constants was the Nice conjecture, which turned out to be not very useful. The constants themselves turned out to have, deep connections to various algebraic geometry questions. So people have been studying this, and there is an active area of work on this. So let me just quickly mention some things. So Seshadri constants on surfaces can be arbitrarily small, and this example can be sort of modify it to get this on any variety of any dimension. So the crucial thing is to do on a surface, but you can generalize this definition, this construction. So Seshadri constants can be very small at specific points. However, there is something interesting about this behavior as shown by them in 1993. So X is on the surface now. So what they showed was, while the Seshadri constant at arbitrary point is arbitrarily small, it is greater than or equal to 1 for, let's say, a very general point. X. So I'm going to use this terminology particularly outside a countable, in this case, countable set of points. In general, it's outside a countable proper closed sets. For a single point, it is just outside a countable set. So this is sort of the first fundamental result in the subject. Though the Seshadri constant is small in complete generality, it's sort of the being small is a special property. It is not what you would expect. It is at least 1 for a very general point. So on any surface, they proved it. In the same paper, they took the example of Miranda and say that it's in general not true that Seshadri constants are bigger than 1, but this is true for general points. So this is sort of the background and some, before I continue, let me just write down maybe 3 questions or 4 questions about these constants which sort of guide one strand of research on this subject. So first question is Lazarsfeld's conjecture, it's called. So if it says that if X is now n-dimensional, L ample, smooth projective variety over complex numbers. That's still the condition. Then okay, so I'll simply say that for very general point. So this is a conjecture. Lazarsfeld have proved this conjecture for surfaces, and Lazarsfeld conjectured this for higher dimension. So I am being a little sloppy about what general means, but actually it means that outside a countable union of curves. Yeah. So yeah, let me just write countable union of curves. This is what is expected here, but actually Lazarsfeld proved that it's outside a countable set. So, but to be sort of consistent, let me write like this, which is not expected for a higher dimension, but it's what. Yeah. Yeah, so it could be proper closed subsets, countably many proper closed subsets. See, on a surface, it is only curves, but again, I'll write countable union of so this conjecture is open. There is some partial evidence towards this, but in general, it is open. For example, I want to build, I'll simply write this is much weaker than what is expected, but still some bound. That's true in all dimensions. Second question is, so there are certainly possible that are irrational. The infimum of some rational number, so it is possible that they're irrational. In fact, it's not known that they can be rational, but Lazarsfeld says that it will be very surprising if they're all rational. So it's expected, let's say, that they're irrational, but we know of no single example, not even one example of. So I'll just sort of indicate one specific situation where one expects this is. Let's say you take a very general hypersurface of degree b at least 5. In fact, let me just even say 5. So if you take a very general hypersurface of degree 5 in P3, you have Picard rank 1, and self-intersection 5. Remember that there is a band, global band for Seshadri constant, which is root 5, but it's exactly equal to root 5. This is a conjecture. I mean, let's say I'll call it a conjecture. People expect this is one instance of irrational Seshadri constant. Of course, not known, but it's if you want to find an example of an irrational Seshadri constant, you can start here. The question which, yeah, so for a general point, yeah, for some point, that's fine. Greater than or equal to 1. Certainly not 1, yeah. Yeah. For some point, but this is for a very general point. So I will not write this, but Seshadri constants as a function of the point x, they are like lower semi-continuous functions. So they are sort of big at general points, small at special points. As the example of Miranda showed, where it can be very small for a special point, but Lazarsfeld has shown that in Lazarsfeld that they are big for a general point. And it's not a sort of a continuous function, it's a discrete function. It will be mostly the maximum value will be attained at a large open set and some discrete set of points where it will be smaller. Root 5 is certainly the upper bound. It may be that it is less for some points, but you want equality for some points at least. Equivalently for a very general point. Okay, so one more question that sort of studied a lot. Yes. Yeah, so that's not supply. I mean, that's not very deep, I would say. I mean, it's standard folklore statement. So one can define the Seshadri constant of X, a variety itself. You can take all ample bundles and all points. So it is certainly true that epsilon of each individual number there is a positive integer, positive real number. But infimum can very well be 0. So now the question is, can okay. So again open, all three are open questions. So we don't know of any variety for which this is 0. I think there is not much clarity on what is expected here. So I will not make any statement. Here it is expected that they are irrational often. There, I don't know whether they can be 0 or not. Yeah, power is just gets multiplied by. So this is because the ratio, if you look at, L dot C gets replaced by B dot C. The multiplicity does not change. So it is just a multiple of that. You can't say for L1 plus L2. There is bound that you can say, but not inequality. Okay. Yeah, so yes, people have studied extensively classes of varieties, including abelian varieties. So there are all kinds of results. I have not sort of prepared a summary, but you know, whether bounds are known. Nothing to answer these questions, but fairly strong results are known for abelian varieties. Yeah, it is certainly possible that it is all known examples, it is positive. So, for example, E of P2 is 1, epsilon of P2 is 1, because we know that epsilon of every ample line on P2 is very ample, and it's at least 1 always. So, this is, so what I really mean is that we do not know of any example where epsilon x is 0. We know of a lot of varieties where epsilon x is known, and it is known to be positive. Yeah, so that also you can do. Correct. So some kind of birational class or something you can do. Not that I know. Yeah, not directly. Like related to the converse that you were saying. I don't know. So actually what I would say is that I have heard people say that this can very well be 0. Epsilon x can be 0. We don't know of an example, but maybe it is 0. Okay, so I'm almost out of time, but I think I started at 10 minutes past now, so it's like 14 minutes left, which I'll make use because I have just done 10% of what I was planning. So, but I will not do all at 90%, so that I promise. So a lot of work in the last, let's say, especially last 25 years, but mostly last 35 years is focused on these questions. Okay, so I don't have much time to talk about this, but let me just try to say orally. So people have studied abelian varieties, Taylor varieties, Palmer varieties. So any class of varieties where there's some additional structure to work with, homogeneous varieties. I mean, extensive studies. Rational surfaces, blow-ups of P2 have been studied extensively. In fact, the best known results are for surfaces. Higher dimensional varieties, not that much is known, except outside these classes of special varieties like abelian, toric, and so on. Okay, so now I will. Okay, so I have to choose what to do in the remaining 30 minutes. So let me just talk about the vector bundle analog. So there is also Seshadri constants vector bundles of arbitrary rank. So we have looked at line bundle case. So this is mostly from a paper of Haycon in 2000, where he defined, so this is 10 years after when I proved Seshadri constants of line bundles. So he defined for arbitrary vector bundles. I'll also write another important paper in this subject is Fulger, and which is 5 years ago, where many of the results of Haycon have been extended or put in more general context. So we have now sort of clearer idea of what vector bundle case is. So I'll give you so X will continue to be a smooth projective variety of dimension n for over complex numbers. But E is a vector bundle of arbitrary rank. So there are several definitions. One which is, I think, simplest to state in the remaining time is the following. So you fix a point. So if you recall, how do we, that positivity adjectives that we have for line bundles, ample, very ample, globally generated, also are defined for vector bundles. And the way it is done, standard way it is done, is you take the projective bundle and take the O1. Adjective, you say E has that adjective. O1 is ample, if then E is ample. So we do the same thing, except that there is a small issue, which is that we want to define the Seshadri constant of the vector bundle at a point, which is on the variety. So if you take the projective bundle and you take O1 of this, it's perfectly valid to look at and define something for E, except that the point is not on this variety. So you can't just, you have to think about what to do. definitions, it turned out that the equivalent that I will write now is the one which is sort of closest to the line bundle case. So let's do the following. So we will work with one, but the point is downstairs. So what I'll do is I'll take A1, but intersect that with curves. Obviously C prime will be curve in the projective bundle. But what we do is divide by so push the curve forward. So C prime is here. So when I do this, I want to ensure that the curve, push forward curve contains the point and it is a curve. So I can achieve this by saying that C prime intersects the fiber, which will guarantee that X is in the push forward. And I'll also require that it's not contained in the fiber, which will guarantee that the push forward is a curve. So I take this. Yeah. So this is, it turns out that if you take a line bundle, this definition gives exactly what we want, because then the projective bundle is just X itself, and you are taking the usual definition. And I'll write one more definition, which sort of works at the variety itself. So we have a curve here, and then I'll take its normalization. Let me call that C tilde. And let's call the composition, let's say mu. So I'll take, so E is a vector bundle on X. I push it all the way back to C tilde. It's a vector bundle on the smooth curve. And I take mu min of this. So the minimum slope of a quotient divided by multiplicity. So the point is here. So it requires some work, but you can prove that these are actually equivalent. So in some sense, the calculation of the vector bundle Seshadri constant reduces to some kind of mu min calculation. And on a surface, for example, one can think about what this means. Okay, so now, unlike the line bundle case, which were not that interesting for a curve, vector bundles on curves can be studied now, because vector bundles on curves have interesting non-trivial Seshadri constants. And one immediate thing you'll see is that if X itself is a curve, smooth curve always, we take smooth varieties. So then there is, this whole picture is just X. So it's just the mu min. So this is proved by Haycon. When X is a curve, so okay, so this is one of the first results. Okay, I'll just write one more, which. So that is just a statement about mu min. So you can prove these results. So this is what we did in 2020. And we also proved that if E is globally generated and ample, so this was the state of affairs for a long time. So mostly curves have been studied. So in the 5 minutes it's left. So the vector bundle definition came in 2000, but really the most interesting work is in the last 5 years after this. So I should not say a lot of work was done, but activity on vector bundle case in the last 5 years. And the way that we work on vector bundle case is that we need some additional structure without which even some very basic questions seem to be impossible to answer. So let me just write one of the open questions and then talk about maybe some results. So if you take x to be P2, so on P2, as we have said a few times, for the line bundle case, there is nothing to do. Seshadri constants of line bundles are completely well understood. But if you give one more rank 2 vector bundle. So also I should remark that if the line vector bundle speaks as the direct sum of line bundles, it's not interesting to study because the Seshadri constant of the vector bundle should be the minimum of the Seshadri constants of the constituent line bundles. So the interesting case to study is not indecomposable vector bundles. So let's take a rank 2 vector bundle. And the question that I've been thinking about is to answer the following question. So, just because the line bundle case on P2 is quite simple, and it is true, in fact, for line bundles, this is the case. So can we answer this? So this is not known. So this is something that we are trying to think about. What is known is if, so this is not known. Not known in full generality. The one reason that it is not known is that we don't really know anything about vector bundles in this sense. We do know a lot about vector bundles, but it's not like there's a structure theorem about them or saying that a vector bundle must come in this exact sequence or it has some other property. We don't know such a statement for an arbitrary vector bundle. Whenever we have such a statement for an arbitrary vector bundle, we can prove this. So one of the cases that we have studied is for toric varieties. If X is a toric variety and the vector bundle in question is a torus equivariant vector bundle, then one can show fairly strong results about Seshadri constants of those. Okay, so when X is toric variety and the vector bundle is an equivariant vector bundle, so that was done by Hevin, Mushtaq, and Pune. So one looks at every toric variety as a finite collection of torus invariant curves, which are all P1s. So actually what you have to do is take the vector bundle, restrict to those finitely many P1s, where the vector bundle will split, and you have a bunch of shifts, and the Seshadri constant is the minimum of those. So, and with Nagaraj, I put some results for flag varieties, same kind of results, invariant torus invariant vector bundles, and with symptomatic we put for longitudinal compactifications and Watt's dimension varieties, similar results were some results for equivariant vector bundles and bunch of this kind. I will just end by saying that all results that are known for vector bundles may use of some additional data, equivariance, or we also worked on something called a Fano vector bundle. So we say a vector bundle is Fano, the projective bundle associated to it is Fano. So there is some structure theorem for such things on projective spaces. So using that structure theorem, we could prove bonds of this kind. But without some additional information, the general picture seems quite obscure. So one needs to think of some new ideas to solve this, I think. Okay, so I'll stop here. Thank you. No, not even for general point. So that would also be interesting, yeah. Yeah, my guess would be that it should be true if you can prove for general point because of P2. It should be possible to do the same argument for any point. In P2, in some sense, there's no difference between any 2 points. Yeah, of course, the homogeneity will not respect E, but still, yeah. I could be wrong, but I would feel that on P2, the Seshadri constant should not see difference between 2 points. in all cases, I mean, people have looked at general type, K3, NDK. So in that sense, people have worked on all these cases. Yes. Typically, one only has some bounds. So Seshadri constants have this, they live in this interval, right, on a surface, let's say. This interval, they're positive but less than square root L square, less than or equal to square root L square. So what people have done is narrowed that interval down. So maybe they give better lower bounds and better upper bounds. Only in very rare cases you know the exact value. Yeah, so there is much more complicated churn numbers and so on. So I cannot write it immediately, but I can. Yeah, so unfortunately I have not written down, but yeah, there is a version of this for vector bundles. Yes, square root L square gets replaced by some other number. New question. What? I see. No, I don't know. I see. I don't, I mean, I have not seen anything, and I don't think anything like this has been done because the situation for vector bundles is at a very preliminary stage. So yeah, short exact sequence, there are relations. So Seshadri constant. Yeah, so Seshadri constant of the middle one is greater than equal to the two things at both ends. But again, there are only bounds, and except in special cases, there is no equality. But such things have been done. I mean, yes. Yes, yes. If there is some structure like that, yes, we can do that. Yeah. Even for rank 2, as I wrote, it's not clear. I mean, but I don't know if you can always put that line bundles in. As a, so one has to do something. So they're not all extensions. So it's not clear, but. No, what there is no you mean the one. So this is not for all surfaces, but higher dimension. No. Yeah, I don't think so. So for abelian surfaces or abelian varieties, the x doesn't matter. So it is certainly at least 1. Because epsilon for a particular point is so. Yeah, so I think K3, it's not probably known. They can be small as my example showed, but yeah. Yeah. Yeah, so I should say this. So until I sort of got into results, the definitions all make sense in all characteristics. So not much work has been done because the original motivation is from Fujita and separation of SJets. These are all characteristic 0 phenomenon. But many of the results do hold for characteristic P just because the proofs are all algebraic and there's not much difference. And there is a different version of Seshadri constants called Frobenius Seshadri constants, which was defined by Mustata and Schweid, which use separation of SJets, but in the context of Frobenius maps. So SJets is a map, some local map being surjective, some mod m power s, maximal ideal power s, but instead of m power s, you take the Frobenius power, m power square bracket s. So they have defined using that, and they compared the Frobenius Seshadri constants, as they call them, and the usual Seshadri constants. So there are some bounds. There are some comparisons. Right. So they, obviously, by the nature of the definition, it's extremely algebraic and very complicated local calculations. So that is one direction in which some different phenomenon is there for characteristic peak. I don't know what. Yeah, so that I have not seen. Yeah. 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 So E very ample, there are at least one. One can show that. Yeah. Very ample vector bundles. Seshadri constants are at least 1. Yeah. So one question actually that leads from your question is every vector bundle ample vector bundle very ample? If so, this will become true immediately, but that's not the case. Every ample line bundle is very ample on P2, not so for vector bundles. This is what we latest thing is we know of vector bundles that are ample but not very ample. So we can't immediately conclude that from that. Yeah. Thank you.